Right, previously we defined a circle in terms of something called a conic section, right, where we take a plane and we cut across, we take a section of a cone, a double nap cone that's parallel to the circular base, and it makes a circle. Okay, but in mathematics, just like in English, sometimes things have multiple definitions. A circle is no different. So think about parallel lines. When we define parallel lines, one way to define it is that they're two lines that are on the same plane and they never intersect. You can also define them as being two lines that are equidistant from each other. You can think of it in terms of being on the coordinate plane of having the same slope. So different ways of thinking about exactly the same concept. So circles have a conic section definition, and so do all of these other conic sections, an ellipse, parabola, and a hyperbola. And then all four of them also have something called a locus definition. A locus, all it is a set of points that share a common geometric property, a locus. Not the bug that has a T on it, it's called a locus. So let's examine this circle and think about what do all the points on the circle have in common. So, no, not green. How about blue? Let me pick a whole bunch of points here, like A and B and C, D, E, and F. All of these points, they're on the circle. What do all of those points have in common? They are all the same distance from this center point here. Right? And that distance, of course, is called the radius. And this h comma k, we're using this as the center point. Very common thing to do. As a matter of fact, in your homework this evening, you're going to be doing something very similar with the parabola. H and K are going to come in there with a vertex. So H and K is a very common set of variables that we use for things. Okay. All right. So now we're going to use this idea of a locus and saying that all of these points that are on the circle being the same distance away, we're going to use that to formally define what a circle is. As a matter of fact, this is basically the definition that we talked about at the very beginning of the year for a circle. So a circle is a locus of coplanar points. Pause for a second. Locus, of course, means a set of points that have something in common, some geometric property in common. And coplanar means that they're all on the same plane, that are equidistant from a given point on called the center. So let's look at the circle as it's drawn here. XY is supposed to be just a generic point. XY represents every single point that's on this circle. And then HK is a static point. It doesn't change. It's the center of the circle, and we usually use H and K for the coordinates, just to refer to them. Of course, you're going to be given numbers, like 3,5 or something, right? All right. So what we're going to do is we're going to use this locus definition to come up with an algebraic equation for a circle in the same kind of way that you do for a line or a parabola or something like that. Okay. Use the locus definition to derive the equation of a circle. Okay, so what we said is that every single point that is on the circle, and this is our generic point. What that means is that it represents every single point that's on that circle, okay? And then we're saying that that point, wherever it is, will always be the distance r away from the center point. So how do I measure distance in the coordinate plane? Don't I have a formula for that? I think so. I think it's called the distance formula. Let's start there. The distance formula. Reviewing that, it goes like this. The distance, let's say between any 2 points, is equal to square root of the difference of the x's. So x1 minus x2 squared, plus the difference of the y's. y1 minus y2, also squared. And remember where it came from. Like we proved this. We derived this earlier this year. Where it came from was the Pythagorean theorem. Pythagorean theorem. This is the connection that circles get to right triangles, right? If I were to draw in a right triangle right here, wait, I want to change this to like red for the right angle. There we go. Perfect. Okay. And Here would be our C. Let's say this down here is our A, and this is our B. We have A squared plus B squared here. We take the square root of that, and we're going to get our C. That's where we're going to apply in order to come up with the equation of a circle. We're just going to plug in this generic point x comma y, and then the center point, which would be a static point. It would be something that they gave us coordinates for, like I said, maybe 5, 6 or something like that. And we're just finding the distance between those two things and setting it equal to r. Whoops. Okay, so r is our distance. Should be equal to the square root of, let's take the difference of our x's, and it really doesn't matter what order I subtract these in. Yeah, nice. But usually we put the variable first. Remember, x is the variable, the h is not. It's a constant number. It would be x minus h squared plus, and now I'll do the same thing with my y's. The y minus the k, and I'll square it. All right, and then, I mean, I could leave it like that if I wanted to, but I ordinarily do not. Instead, what we do is we square both sides of this. So if I square that side and square that side, it gets rid of the square root. And so I can see that I can get r squared is equal to x minus h squared plus y minus k squared. And now its connection to the Pythagorean theorem is even more obvious, I think. Here's our c squared, here's our a squared, and here's our b squared. Okay, so ordinarily, the r squared that's over here on the left-hand side, we switch it over to the right-hand side. It really doesn't matter. I mean, it's honestly doesn't really matter because it's an equation. It obeys the symmetric property. But ordinarily, we flip it around so it looks like this. So let's look at the different parts of the equation as we just came up with it for a circle. X minus h quantity squared plus y minus k quantity squared is equal to r squared. So notice that in this equation, the h and the k, they have a little subtraction sign right out in front of it. And so sometimes that confuses people when they try to figure out what the center of that circle is supposed to be. So let's take a look at an example here. So let's say, as an example, we have the equation x minus 4 squared plus y minus, no, let's make it plus 1 squared is equal to 36. That's the equation that you'd be given. We would recognize it as a circle, and we'd want to be able to figure out what's the center of that circle and what's the radius of that circle. So we can see that just lining up our stuff, that our center of our circle has something to do with a 4 and a 1. But now we have to figure out the signs. So I'm going to relate this to you with point-slope form. So remember, point-slope form for a line is y minus y1 is equal to our slope times x minus x1. And notice that the y1 and the x1, they already have minus signs in front of them. If I were to, let's make something up, x minus 2 is equal to some sort of slope like a third, x plus 4, then the point that this goes through has something to do with 2 and 4, right? Except for it doesn't have those same signs. It's not, yikes, it's not positive 4 and negative 2. That is incorrect. Instead, it is negative 4 and positive 2, right? Because the negative sign's already there. You can see the negative sign's already there, and the y1 is just 2. Over here, this negative sign's already there. In other words, this must have been minus a negative 4. So the same thing is happening here on the center. When this says x minus 4, our center point has an x-coordinate of 4. And when the second term says y plus 1, this must have been minus a negative 1, and so our y-coordinate is negative 1. So there's our center point. The 36 that's over here is equal to r squared. So to get r, you would take the square root of that, and your radius is actually 6. So it has a center of 4, negative 1, and has a radius of 6. In the next video, what we will do is put these things together to write and graph some equations.